In this example, we want to look at the conservation of energy with a 0.5 kilogram cart sitting at rest against a wall. This particular cart has a little spring-loaded plunger in it that's engaged. The spring's compressed about 0.05 meters in here, and we want to see what happens to this cart as it rolls along the ground here after that spring is released. We want to see how fast it's going along the way here, and then as it rolls up the incline, we want to see about how high up the incline it's going to go, meaning when it reaches a speed of 0 up there, what's its vertical displacement from the ground where it originally was rolling along here. Let's go ahead and get started with this. First thing we're going to need to do is find the total energy that the cart has right now as it's against the wall. So our total energy is our kinetic energy plus our gravitational potential energy plus our elastic potential energy. Now we see it's not moving, so we know it doesn't have any kinetic energy. It's on the ground, so we'll say that's 0 gravitational potential energy. So all we have is elastic potential energy, which is going to be equal to our total energy of the cart right now as we get things started. So the energy, we'll start filling things in here. The energy is equal to the two zeros plus the equation for our elastic potential energy, 1/2 spring constant times the displacement squared. So we just start filling this in here. So we've got 1/2 times that 2744 newtons per meter times the 0.05 meters squared. So if we work all that out there, we end up with an energy of 3.43 joules, all contained in that cart just sitting there right now. So the energy is going to be conserved. So if we follow the cart along, it should still have an energy of 3.43 joules as it's moving along the ground here. And then as it rolls up the hill, every point along the way, and when it gets to the top up here, still going to have a total energy of about 3.43 joules. Alright, so now the cart has been launched off of the wall here. It's cruising along to the right. And so now we want to look at the speed that it's going to have. In order to do that, we want to find the kinetic energy, because that's the energy of motion. So again, there's no gravitational potential energy. Now there's no elastic potential energy. So at this point, our total energy that we had to start with will be equal just to our kinetic energy. So again, we'll fill in all the pieces there in our equation. We have our 1/2 mass times speed squared for the kinetic energy, and then we put in some zeros for our two potential energies in this case. Go ahead and put in our energy. We'll substitute in our mass of 0.5 kilograms and do a little math here. So now we take our 0.25 kilograms, cancel that out on both sides, and we end up with 13.72 joules per kilogram equals our speed squared. What is a joule per kilogram? So we have a joule, which is a newton times a meter. The newton is the kilogram meter per second squared times a meter. You combine all that, we get a kilogram meter squared per second squared. That's the joule. Now, put the joule per kilogram with kilogram meter squared per second squared divided by kilograms. The kilograms cancel out, leaving you with meter squared per second squared. So now our V squared is, as we just determined, 13.72 meters squared per second squared. We'll take the square root of both sides of that in order to solve for the speed, which works out to be about 3.7 meters per second. The last question that we had then was to use the energy conservation. We want to find out how high the cart rolls up the incline. So we know at the top here we're going to have a speed of 0. So that means our kinetic energy is going to be 0. Again, there's no elastic potential energy. We've released the spring. That's not doing anything anymore. And our total energy here then is simply going to be equal to our gravitational potential energy. Now let's go ahead and substitute everything into our energy equation. We have no kinetic energy, no elastic potential energy, and our gravitational potential energy is mass times the acceleration due to gravity times the vertical displacement. So we have our 3.43 joules of energy, we have our mass of 0.5 kilograms, 9.8 meters per second squared is the acceleration due to gravity, and our vertical displacement. The 0.5 kilograms times 9.8 meters per second squared is about 4.9 kilogram meters per second squared, so that'll cancel out on the right side, and we'll divide that over on the left side as well. And so we're ending up with a unit there of joules per kilogram meter per second squared. So as we just determined, then the vertical displacement works out to be at 0.7, and the units would be meters. The units of joules per kilogram meter per second squared. A joule is a newton times a meter. Kilogram meter per second squared is a newton. So the newtons would cancel out. That leaves you just with meters. Now that we know the units are meters, just simply divide 3.43 times 4.9 and we get 0.7 meters. So if you use the same basic process for all the different conservation of energy problems, whether it be things rolling down ramps, up ramps, pendulums swinging back and forth, even roller coasters. It's all the same basic process. You have total energy is your kinetic plus your gravitational potential energy plus your elastic potential energy. In these examples, we only had one of each of those on the right side there, but in some cases you'll have multiples of those, if not all three. But in either case, the energy is always conserved throughout the entire process.